Section 10.4 is about areas and lengths in polar coordinates. So this is just like when we learned about parametric equations. We finished that section by learning about all the different things that we've done in Calculus 2 so far if we were in parametric equation land. So that is what section 10.4 is, but for polar coordinates. So we're going to start out with areas. So first, we need to figure out how we know what the area under a polar curve would be versus a Cartesian coordinate system curve. So we need to know the formula for the area of a region whose boundary is given by a polar equation. So to do that, we use the area of a sector of a circle. A sector means part of a circle. So if you look at this shape at the bottom of the screen, it sort of looks like a slice of pizza. And you could think of it exactly that way. If this were an entire pie, an entire pizza, and you cut out one slice of it, how do I know the area of that slice of pizza? Well, the formula for that, which is known, and you may have used it when you were in pre-cal, is 1/2 r squared theta, where r is the radius of the circle, and theta, of course, is the angle, just like we're using in polar coordinates. So if we consider a region R that is traced out by an actual polar curve, f of theta, and we have the rays theta equals A, which is this line at the bottom, and theta equals B, so we have two different angles. And f is a continuous function, f is this top blue curve. How do we figure out the area of this region, capital R? Well, just like any other times we've talked about area, we need to divide the interval from A to B into subintervals, just like we did with the rectangles with regular functions. So if you divide our region based on a bunch of different angles, that's what all the black lines are, several different angles, theta, or theta I minus 1, like you see on the screen, and we choose one in there, then we can use the standard Riemann sum idea to figure out what's the equation that represents the area under this curve. So the area of one of those pieces, one of those slices, could be approximated as 1/2 r squared theta, just like we saw in the beginning, 1/2 r squared theta. So we have 1/2 r squared will become f of theta squared. And then of course, like we've seen all the time, we have delta theta, which eventually will become d theta in the integral. So if we use the same idea and take the sum of all these approximations from 1 to n, what do we end up with? An integral. So the limit of the Riemann sum is the definition for an integral, so we can turn this Riemann sum into an integral from a to b of 1/2 r squared d theta, where r is f of theta. And I know I'm going kind of fast, but I want to get you to the final result rather than focus too much on the derivation. So the easiest way to remember this formula is with the r instead of the f of theta. So 1/2 r squared is what you're integrating to find the area under a polar curve from A to B. And you can think of it, let me go back to the picture. Think of it as this picture rather than a standard under the curve on an XY coordinate system, because it's actually being swept out by rays of angles, which is why we have an angular area here instead of a standard rectangular area. So let's look at an example so this makes a little bit more sense. The question says to find the area enclosed by one loop of the 4-leaved rows, which is what we see below, which is r equals cosine 2 theta. Now when they say one loop, they mean what you see in blue here, one single petal of the flower. We just want the area under or inside of that loop, you could say. So the first thing we have to figure out is what our limits of integration would be, and that's a totally different thought process here. If this were a function, which of course it's not because it miserably fails the vertical line test, you would think that you would go from the origin out to the right-hand point of this flower. But this is technically polar coordinate system, which is determined by angles. So instead, we have to think about what are the boundary angles that enclose this loop of the flower, this petal of the flower. And you can see what's drawn here is the bottom boundary could be considered to be negative pi over 4, and the upper boundary would be positive pi over 4. This loop is completely contained in between those two angles. So that is going to be our A and B, our limits of integration. So the formula, remember, is 1/2 r squared. So our r is cosine 2 theta. So we have the integral from negative pi over 4 to pi over 4, that was our boundary angles, of 1/2 r squared. R squared would be cosine of 2 theta all squared. So on the second line, you can see we've brought the 1/2 outside of the integral and written cosine squared of 2 theta. So ultimately, we need to determine how to integrate cosine squared 2 theta. So if you'll remember from the past, we have reduction in power formulas, which we also called double angle formulas, that will allow us to rewrite cosine squared as something without a square. And in this case, cosine squared becomes 1 plus cosine. This 4 theta comes from the original 2 theta here, because the double angle formula says that cosine squared of theta is 1 plus cosine 2 theta. Well, we already started with 2 theta, so when we use the formula, it becomes 4 theta. We've doubled it. So this comes from the double angle formula. And then the 1/2 is the double angle formula as well. 1/2 times 1 plus cosine 4 theta. So now that's something we can actually go ahead and straight figure out the antiderivative of. So we've pulled the 1/2 out front from the double angle formula. 1 becomes theta. That's the antiderivative of 1. Cosine turns into sine. And remember, this 1/4 comes from the reverse of the chain rule, where we have to account for the fact that if I were taking the derivative of sine 4 theta, it would become cosine 4 theta times 4 for the chain rule. So this 1/4 counteracts that 4. And then once you plug in your limits of integration, we end up with an answer of pi over 8. Okay? So let's stop this video there, and then we'll move on to arc length in the next video.